1879, Hartford, Connecticut. The measurement crisis that threatened to destroy American manufacturing was hiding in plain sight. European master craftsmen could hand-fit parts with tolerances of maybe 100 micro-inches on their finest days. American factories were struggling with measurements that varied by thousands of micro-inches. A 12-inch gun barrel from one factory wouldn't fit a 12-inch receiver from another. British trade journals called American precision crude approximation masquerading as science. German engineers shook their heads at American mass production dreams. The French inventors of the metric system dismissed American measurements entirely. Then two men walked into the Pratt Whitney workshop with an impossible promise. William Rogers, a Harvard astronomy professor, and George Bond, a Stevens Institute graduate, claimed they could build a measuring machine accurate to 20 micro-inches. That's precise enough to detect the expansion of steel from human body heat. European experts laughed. Physics itself seemed to prove them wrong. Temperature changes, vibrations, and humidity made consistent micromeasurements impossible, but deep in a climate-controlled Hartford workshop, something extraordinary was taking shape. The machine that would make European precision engineers question everything they thought they knew about measurement. The morning fog clung to Hartford's factory district as Francis Pratt stepped through the gates of his precision tool workshop, the October chill of 1879, carrying with it the familiar sounds of American ambition grinding against European ridicule. Steam hissed from the heating pipes that ran along the brick walls, while the rhythmic hammering of drop forges echoed from neighboring buildings where manufacturers struggled with the same crushing reality that kept Pratt awake most nights. American mass production was drowning in its own inconsistency. Pratt paused at his office window, watching workers carry steel components between buildings, each piece supposedly machined to identical specifications, yet requiring individual hand-fitting before assembly. The irony burned deeper each morning. His company, Pratt & Whitney, had built a reputation manufacturing precision tools and machinery, yet they couldn't solve the fundamental problem strangling American manufacturing. There was no standard inch. Every factory, every craftsman, every measuring device operated with different definitions of basic measurements. A 12-inch gun barrel machined in Hartford measured differently from a 12-inch receiver produced in Springfield. The tolerances varied by thousands of micro-inches, making true interchangeable parts impossible. The consequences rippled through every corner of American industry. Firearms manufacturers couldn't guarantee that components from different suppliers would fit together. Sewing machine companies faced similar nightmares when sourcing parts from multiple workshops. The emerging bicycle industry struggled to achieve the consistency that would make mass production economically viable. Each finished product required skilled craftsmen to hand-fit components, defeating the entire purpose of machine manufacturing. European competitors observed American struggles with barely concealed satisfaction. British trade journals published scathing assessments of American precision, describing it as crude approximation masquerading as science. German precision engineers, who had spent generations perfecting mechanical measurement techniques, shook their heads at American attempts to rush processes that required patient refinement. The French, inventors of the metric system, dismissed American measurement standards as fundamentally chaotic. The technical challenges seemed insurmountable. Existing measuring devices drifted with temperature changes, shifted with building vibrations, and fluctuated with humidity variations. Even the basic definition of an inch varied from city to city, as local standards had evolved independently without central coordination. Master craftsmen in Birmingham and Liège had developed measurement techniques over centuries of apprenticeship, achieving tolerances through hand-eye coordination and tactile sensitivity that machines couldn't replicate. European armorers in particular took pleasure in American measurement failures. They had perfected individual hand-fitting techniques that produced firearms of exceptional quality, with each component carefully adjusted to work with its specific partners. Why rush toward machine production when traditional methods guaranteed superior results? Their workshops operated like medieval guilds, with knowledge passed down through generations of craftsmen who understood precision as an art form rather than an industrial process. The numbers told a devastating story. European master gaugers could work to tolerances of perhaps 100 micro-inches on their finest days, using techniques refined through decades of experience. American measurements, by contrast, varied by thousands of microinches even within individual factories. The gap wasn't merely technical, but philosophical. Europeans viewed precision as the culmination of human skill and patience, while Americans sought systematic methods that could be taught and replicated. Pratt understood the stakes extending far beyond his own company's success. American industrial independence hung in the balance. The nation that had fought for political freedom remained economically dependent on European technical superiority. If American manufacturers couldn't achieve consistent precision, they would forever occupy secondary positions in global markets, assembling products designed and perfected elsewhere. The financial pressures intensified daily. Government contracts demanded interchangeable parts, but contractors couldn't deliver without reliable measurement. Standards. Military officials, having witnessed multiple failures of American precision manufacturing, grew increasingly skeptical of domestic suppliers. The United States Army Ordnance Department maintained relationships with European armories precisely because American companies couldn't guarantee the consistency that military applications required. Pratt's partner, Amos Whitney, shared the frustration that drove their search for solutions. Both men had left secure positions at Colt Manufacturing to establish their own company, betting everything on American systematic manufacturing. They believed that systematic engineering could surpass traditional European craftsmanship, but belief alone couldn't overcome the measurement crisis paralyzing their industry. The breakthrough would require approaching measurement with entirely different assumptions. Instead of trying to perfect human technique, they needed mechanical amplification systems that could detect variations invisible to human senses. Instead of fighting environmental factors like temperature and vibration, they needed compensation mechanisms that accounted for these variables systematically. The solution demanded collaboration between theoretical knowledge and practical engineering. Academic understanding of precision measurement needed to merge with workshop experience of manufacturing realities. The challenge wasn't simply building better measuring tools, but creating entirely new approaches to mechanical precision that could surpass centuries of European craftsman tradition. As 1879 drew toward winter, American manufacturing stood at a crossroads. European critics seemed increasingly vindicated in their dismissal of American precision capabilities. The technical obstacles appeared too fundamental to overcome through American methods of rushing toward systematic solutions. Yet in workshops across Hartford and beyond, engineers refused to accept European superiority as permanent. The stage was set for either spectacular failure or revolutionary breakthrough that would redefine precision measurement forever. William Rogers arrived at the Pratt & Whitney workshop on a crisp November morning in 1879, carrying leather satchels filled with astronomical instruments and notebooks, dense with calculations that had guided Harvard's telescope measurements for the past decade. The Harvard astronomy professor moved through the machine shop with the careful precision of a man accustomed to detecting celestial movements measured in micro-arc seconds, his trained eye immediately recognizing the mechanical chaos that plagued American manufacturing. Steam hammers shook the building's wooden floors, while workers struggled with measuring devices that drifted with each temperature fluctuation. Yet Rogers saw possibilities where others saw insurmountable obstacles. George Bond emerged from the workshop's rear section, wiping machine oil from precision calipers that represented the current limit of American measurement capability. The Stevens Institute graduate had spent months studying the fundamental physics of mechanical measurement, documenting how existing tools failed under the environmental pressures of industrial production. Bond approached Rogers with the directness of an engineer who had learned to communicate through demonstration rather than theory, immediately leading the professor to a workbench where half-assembled measuring devices revealed the scope of their challenge. The two men represented complementary approaches to precision measurement that had never been systematically combined in American manufacturing. Rogers brought theoretical understanding of measurement amplification derived from astronomical observation, where detecting stellar parallax required mechanical systems that could translate invisible movements into observable results. Bond contributed practical engineering knowledge of manufacturing environments, understanding how temperature variations, building vibrations, and humidity changes affected mechanical stability in real workshop conditions. Their initial conversations revealed the magnitude of innovation required to achieve 20 micro-inch accuracy. Rogers explained how astronomical measurements use differential techniques to cancel out environmental variations, employing mechanical compensation systems that automatically adjusted for temperature changes and atmospheric pressure fluctuations. Bond recognized immediately that similar principles could address the fundamental instability plaguing manufacturing measurement if they could design mechanical amplification systems robust enough to function in industrial environments. The breakthrough concept emerged during their third week of collaboration. Instead of fighting temperature changes that caused metal expansion and contraction, they would design materials combinations that naturally compensated for thermal variations. Rogers had observed similar principles in telescope mounting systems, where brass and steel components were deliberately chosen for their different expansion rates, creating mechanical stability across varying temperatures. Bond realized that applying these astronomical techniques to manufacturing measurement could achieve consistency impossible with traditional single-material tools. Their design approach borrowed directly from stellar measurement methodology. Astronomical observations required detecting movements smaller than mechanical tolerances could normally measure, using leverage systems that transform tiny variations into visible displacements. Rogers proposed mechanical amplification ratios of 1,000 to 1, where a 20 microinch variation would produce a 20,000th inch movement detectable by conventional observation methods. Bond recognized that such amplification required precision ground surfaces and mechanical linkages engineered to tolerances far exceeding current American manufacturing capabilities. The differential screw mechanism became their central innovation. Rogers had used similar devices to adjust telescope positions with extraordinary precision, employing threaded components with slightly different pitches to create fine adjustment capability. When two screws with nearly identical thread pitches were mechanically linked, their differential motion could be controlled to micro-inch precision. Bond adapted this astronomical technique for comparative measurement, designing systems where unknown dimensions could be compared against known standards with unprecedented accuracy. Material selection demanded careful engineering that combined Rogers's theoretical knowledge with Bond's practical experience. They chose brass components for their stability and workability, combined with hardened steel surfaces for wear resistance and dimensional accuracy. The thermal expansion characteristics of these materials were calculated to provide natural compensation across the temperature ranges typical of manufacturing environments. Rogers applied heat transfer equations derived from observatory environmental control, while Bond contributed workshop knowledge of realistic temperature variations in industrial settings. The mechanical amplification system required precision grinding techniques that pushed American manufacturing capability beyond existing limits. Each contact surface needed to be finished to tolerances measured in fractions of micro-inches using grinding and lapping processes that Bond developed specifically for their project. Rogers contributed theoretical understanding of how surface irregularities affected measurement accuracy, derived from his experience with telescope mirror surfaces where microscopic imperfections could distort stellar observations. Environmental isolation became another critical design element. Rogers understood from astronomical work how external vibrations could corrupt precise measurements, requiring mechanical systems isolated from building movement and machinery vibration. Bond designed mounting systems that provided mechanical stability while allowing the necessary adjustments for comparative measurement operations. Their isolation techniques borrowed from observatory practice, but adapted to manufacturing environments where complete vibration elimination was impossible. The temperature compensation mechanism represented their most sophisticated innovation. Rogers calculated thermal expansion coefficients for their brass-steel combinations, designing mechanical linkages that automatically adjusted for temperature variations without requiring manual correction. Bond engineered the mechanical implementation of these calculations, creating systems where thermal expansion in one component was automatically offset by corresponding changes in related components. By winter's end, their theoretical foundation was complete. The Rogers-Bond comparator design combined astronomical measurement principles with manufacturing engineering in ways that had never been attempted in American industry. Rogers had provided the scientific framework for achieving 20 microinch accuracy through mechanical amplification and thermal compensation. Bond had solved the practical engineering challenges of implementing these techniques in workshop environments where precision measurement needed to function reliably under real production conditions. Their collaboration had produced detailed engineering drawings and mathematical specifications for a measuring machine that could theoretically achieve accuracy surpassing European master craftsmen. Yet theory remained untested by the harsh realities of manufacturing implementation. The next phase would determine whether American systematic engineering could actually deliver the precision that centuries of European craftsmanship had established as the global standard for mechanical measurement. The spring of 1881 brought unprecedented international attention to Hartford's industrial district, as news of the Rogers-Bond comparator spread through engineering circles from London to Berlin. Thomas Henderson, leading a British delegation of precision engineers, stepped off the train at Hartford's Union Station with expectations shaped by decades of European superiority in mechanical measurement. The British team had traveled across the Atlantic expecting to witness typical American overconfidence masquerading as technical innovation, armed with their own precision instruments to expose the inevitable shortcomings of rushed American manufacturing methods. Bond met the delegation at the Pratt Whitney gates, his confidence evident in the unhurried manner with which he guided them through the workshop toward the climate-controlled measurement room that had become the project's nerve center. The British engineers noticed immediately that the Americans had invested considerable resources in environmental controls far exceeding typical manufacturing facilities. Temperature-regulated chambers, vibration isolation systems, and humidity controls suggested a level of sophistication that challenged their preconceptions about American precision manufacturing. The measurement room itself defied European expectations of American workshop conditions. Massive stone foundations isolated the Rogers-Bond comparator from building vibrations, while carefully regulated heating systems maintained temperatures within fractions of degrees. Gas lamps provided steady illumination without the heat fluctuations of conventional workshop lighting. The mechanical precision evident in every component surprised visitors accustomed to American manufacturing environments where speed took precedence over refinement. Henderson examined the comparator's differential screw mechanisms with the skeptical eye of an engineer who had witnessed countless measurement devices fail under rigorous testing. The CIA's brass and steel construction impressed him with its sophisticated understanding of thermal compensation principles, while the mechanical amplification systems demonstrated engineering knowledge that surpassed many European implementations. Yet Henderson maintained professional reservations about American claims of 20 micro-inch accuracy, having learned through experience that theoretical precision rarely survived practical application. The demonstration began with Bond adjusting the comparator to measure standard gauge blocks whose dimensions had been verified by European master craftsmen. The mechanical amplification system transformed micro-inch variations into clearly visible movements on precision dials, while the thermal compensation mechanisms automatically adjusted for temperature fluctuations that would have corrupted conventional measurements. British observers watched in growing amazement as the American device consistently detected variations smaller than their own instruments could reliably measure. Rogers joined the demonstration to explain the astronomical principles underlying their measurement techniques. He described how stellar parallax measurements required detecting angular variations measured in micro-arc seconds, using mechanical systems that amplified invisible movements into observable displacements. The British engineers recognized immediately that applying astronomical methodology to manufacturing measurement represented innovation far beyond typical American approaches to precision engineering. Rogers' explanations revealed theoretical sophistication that challenged European assumptions about American technical capabilities. The crucial test involved measuring components that European craftsmen had hand-fitted to tolerances, representing the pinnacle of Birmingham manufacturing precision. British delegation members had brought gauge blocks and precision components, whose dimensions they considered definitive standards for mechanical accuracy. The Rogers-Bond comparator not only matched their measurements, but detected variations that European instruments couldn't consistently observe. Henderson found himself witnessing precision that exceeded the capabilities of equipment used in Britain's finest workshops. Bond demonstrated the comparator's stability by conducting repeated measurements over several hours, while building temperature fluctuated with changing weather conditions. The thermal compensation mechanisms maintain measurement accuracy despite environmental variations that would have rendered European devices unreliable. British engineers observed mechanical consistency they had never imagined possible, achieved through systematic engineering rather than craftsman skill developed over generations of apprenticeship. The delegation's skepticism transformed into professional admiration as they recognized genuine technical achievement. Henderson privately acknowledged that American systematic methods had produced measurement capabilities surpassing traditional European approaches. The mechanical amplification ratios, thermal compensation systems, and environmental isolation techniques represented innovations that British manufacturing could adopt to improve their own precision capabilities. Yet accepting American technical superiority challenged fundamental assumptions about European manufacturing supremacy. Word of the successful demonstration spread rapidly through international engineering networks. Technical journals in London began publishing detailed accounts of American measurement innovations, while German precision manufacturers sent their own representatives to evaluate Hartford's developments. French metrologists, despite their dismissal of American measurement standards, initiated correspondence with Rogers regarding theoretical aspects of mechanical amplification systems applied to comparative measurement. The Rogers-Bond comparator's reputation reached government procurement offices where military contracts demanded precision that traditional American manufacturing had never achieved. United States Army Ordnance Department officials, having witnessed multiple failures of domestic precision manufacturing, scheduled their own evaluation of the Hartford innovation. Colonel James Whitfield, responsible for firearm component standardization, approached the demonstration with professional skepticism, tempered by hope that American manufacturing might finally achieve European quality precision. European manufacturing facilities began expressing interest in licensing American measurement technology, reversing traditional patterns of technological transfer across the Atlantic. British armories that had dismissed American precision capabilities initiated negotiations for Rogers-Bond measurement systems. German toolmakers investigated importing American comparators to improve their own manufacturing consistency. The technical achievement represented a fundamental shift in global perceptions of American engineering capabilities. By summer's end, the Rogers-Bond comparator had established American measurement technology as internationally competitive with European standards. Henderson's delegation returned to Birmingham with reports that acknowledged American technical innovation in terms that challenged centuries of European assumptions about precision manufacturing. The demonstration had proven that systematic engineering could achieve results surpassing traditional craftsman methods, validating American approaches to industrial precision that Europeans had long dismissed as impossible. Yet success brought new pressures and expectations that would test the innovation's reliability under expanded applications. Government contracts and international attention demanded consistent performance across multiple installations and varying operational conditions. The Rogers-Bond principle needed to prove itself beyond controlled demonstration. Conditions: establishing American precision measurement as permanently superior to European alternatives rather than temporary technical curiosity. The disaster struck on a humid October morning in 1881, when Colonel James Whitfield arrived at the Pratt Whitney workshop with a delegation of Army Ordnance officials whose approval could secure the government contracts that would establish American precision manufacturing as militarily viable. Bond had spent weeks preparing for this demonstration, calibrating the Rogers-Bond comparator to showcase the 20 microinch accuracy that had impressed European visitors throughout the summer. The measurement room's environmental controls had been fine-tuned to maintain perfect stability, while precision gauge blocks verified by multiple international standards awaited testing that would prove American systematic engineering superior to European craftsman methods. The morning began with promise as Bond guided the military delegation through preliminary demonstrations that showcased the comparator's mechanical amplification systems and thermal compensation mechanisms. Whitfield examined the differential screw mechanisms with the professional skepticism of an officer who had witnessed countless manufacturing promises collapse under operational pressure. Yet the initial measurements matched theoretical specifications with consistency that impressed even the most cautious observers. The brass and steel components functioned flawlessly, while precision dials indicated variations measured in fractions of microinches. Then the Hartford Workshop's steam heating system activated for the first time since spring maintenance, sending thermal fluctuations through the building that had never been tested against the comparator's environmental isolation systems. Hot water pipes running beneath the measurement room's floor created temperature gradients that overwhelmed the thermal compensation mechanisms designed for gradual seasonal changes rather than sudden heating system cycles. Bond watched in growing alarm as measurement readings began fluctuating beyond acceptable tolerances, despite environmental controls that had maintained stability throughout months of successful demonstrations. The mechanical amplification systems that transformed micro-inch variations into observable movements now magnified thermal instabilities into erratic dial fluctuations that destroyed measurement credibility. Components that had maintained dimensional stability under controlled conditions began expanding and contracting at different rates as heat from the building's heating system created thermal gradients throughout the measurement room. Bond's attempts to recalibrate the instrument only revealed the extent of thermal instability that threatened to invalidate months of successful development work. Whitfield observed the deteriorating demonstration with the grim satisfaction of an officer whose expectations of American manufacturing failure were being confirmed by direct observation. The Army Ordnance Department had evaluated numerous domestic precision manufacturing claims that collapsed under rigorous testing conditions, and the Rogers-Bond comparator appeared to be following familiar patterns of American overconfidence meeting operational reality. European visitors who had praised American innovation during carefully controlled summer demonstrations would have recognized the environmental instability as evidence supporting traditional craftsman superiority over systematic manufacturing methods. Bond attempted to explain the heating system's unexpected thermal effects, describing how sudden temperature changes overwhelmed compensation mechanisms designed for gradual environmental variations. His technical explanations sounded increasingly desperate as measurement inconsistencies multiplied with each recalibration attempt. The mechanical precision that had functioned flawlessly under stable conditions proved vulnerable to environmental variations that European workshops accommodated through craftsman experience rather than systematic engineering approaches. Rogers hurried from Harvard upon receiving Bond's urgent telegram, arriving to find the demonstration in complete collapse and military officials preparing to recommend against government contracts that represented the project's financial survival. The Harvard professor examined the thermal instabilities with growing recognition that their astronomical measurement techniques required environmental control beyond typical manufacturing capabilities. Observatory conditions that allowed stellar parallax measurements demanded isolation from temperature variations that industrial workshops couldn't practically achieve. The failure cascaded through every aspect of the Rogers-Bond innovation as thermal fluctuations revealed fundamental vulnerabilities in their systematic approach to precision measurement. Mechanical amplification systems that detected micro-inch variations with extraordinary sensitivity also amplified environmental instabilities that craftsman methods accommodated through human adaptability. The differential screw mechanisms that provided unprecedented accuracy under controlled conditions became sources of measurement error when subjected to real workshop environmental pressures. Bond worked 18-hour days attempting to solve problems that seemed to multiply with each attempted solution. Environmental isolation systems that had maintained measurement stability during summer demonstrations failed to accommodate heating system thermal cycles that created temperature gradients throughout the workshop. Mechanical compensation mechanisms designed to offset thermal expansion proved inadequate for managing thermal shock conditions that occurred when steam heating activated after hours of dormancy. European engineering journals began publishing accounts of the American measurement failure with barely concealed satisfaction at the confirmation of systematic manufacturing limitations. British precision engineers who had acknowledged American innovation during successful demonstrations now cited the thermal instability as evidence that traditional craftsman methods remained superior to mechanical approaches. German toolmakers canceled investigations of American measurement technology, while French metrologists dismissed the Rogers-Bond principle as fundamentally flawed for practical manufacturing applications. The financial implications threatened Pratt and Whitney's survival as government contracts that had seemed secured evaporated with the demonstration failure. Francis Pratt and Amos Whitney faced potential bankruptcy if their precision measurement investment couldn't be salvaged through solutions to environmental instability problems that had invalidated months of development work. European competitors who had begun licensing negotiations immediately withdrew their interest upon learning of the thermal control problems that destroyed measurement reliability. Rogers returned to Harvard convinced that the project represented an impossible marriage of astronomical precision techniques with manufacturing environmental realities that couldn't be systematically controlled. The theoretical foundation that had enabled 20 micro-inch accuracy under laboratory conditions proved inadequate for workshop applications where temperature variations, vibration, and humidity changes created measurement conditions far more challenging than stellar observations. His collaboration with Bond had produced remarkable innovation that failed at the critical moment when practical application demanded performance beyond theoretical capabilities. Bond refused to abandon the project despite overwhelming evidence that environmental instability had destroyed the Rogers-Bond comparator's credibility with potential customers and financial backers. He remained in the workshop through winter nights, studying thermal patterns and mechanical responses that had caused the demonstration disaster. His engineering intuition suggested that systematic solutions existed for problems that had defeated their initial approaches, if he could identify the fundamental sources of thermal instability that overwhelmed their compensation mechanisms. The revelation came to Bond during a bitter February night in 1882 as he remained alone in the workshop, studying thermal patterns with instruments borrowed from Rogers' astronomical equipment. Smoke from his oil lamp created barely perceptible air currents that danced across the measurement room, revealing convection patterns invisible during daytime operations when heating systems and human activity masked subtle atmospheric movements. Bond realized suddenly that the building's steam heating created not just temperature variations, but air circulation patterns that generated microscopic vibrations affecting measurement stability in ways their isolation systems had never addressed. The breakthrough understanding emerged from careful observation of how thermal convection interacted with mechanical precision. Steam radiators distributed throughout the workshop created rising columns of heated air that generated atmospheric turbulence, while temperature differentials between heated and unheated surfaces produced air currents carrying microscopic particles and moisture variations. These environmental factors created measurement instabilities that mechanical isolation couldn't address because the problems originated within the measurement environment itself, rather than from external building vibrations. Bond's solution required complete reconceptualization of environmental control for precision measurement. Instead of merely isolating the comparator from external disturbances, he needed to create atmospheric stability that eliminated internal sources of measurement variation. This meant designing climate control systems that maintained not just temperature consistency, but atmospheric stillness, humidity stability, and elimination of air circulation patterns that could affect mechanical precision at the micro-inch level. The engineering challenges demanded innovations that pushed American manufacturing capability beyond existing limits. Bond designed ventilation systems that provided fresh air without creating circulation patterns, using horizontal air movement instead of convection currents that would disturb measurement stability. Temperature control required radiant heating systems that eliminated hot air circulation while maintaining thermal consistency throughout the measurement chamber. Humidity control demanded materials and sealing techniques that prevented atmospheric moisture variations from affecting mechanical components. Rogers returned from Harvard in March with renewed enthusiasm for the project, after Bond's letters described systematic solutions to environmental control problems that had destroyed their initial demonstration. The Harvard professor brought additional astronomical instruments designed for detecting atmospheric disturbances that affected stellar observations, recognizing that precision measurement required environmental control approaching observatory standards. Their collaboration resumed with deeper understanding of how workshop conditions differed from laboratory environments where their original success had been achieved. The reconstructed measurement facility incorporated lessons learned from the demonstration disaster with engineering sophistication that exceeded their original design. Thermal isolation systems used multiple material layers with different expansion characteristics to create temperature stability, while mechanical isolation employed vibration dampening techniques borrowed from astronomical equipment mounting. Environmental controls maintained atmospheric conditions within tolerances measured in fractions of degrees and percentage points of humidity variation. Michael O'Brien, the workshop foreman who had witnessed the original failure, observed the reconstruction with cautious optimism tempered by practical experience of how theoretical innovations often collapsed under production pressures. O'Brien's 20 years of manufacturing experience had taught him that measurement devices needed to function reliably under real workshop conditions, with real workers operating under time pressures that theoretical testing couldn't replicate. He demanded that the reconstructed comparator prove itself through extended operational testing before claiming success. The new Rogers-Bond comparator exceeded its original specifications when testing resumed in spring 1882. Environmental control systems maintained measurement stability despite atmospheric conditions that had destroyed the original demonstration, while mechanical improvements achieved accuracy consistently superior to 20 microinches. Bond's systematic approach to environmental control had solved problems that European craftsman methods accommodated through human adaptability, proving that American engineering could surpass traditional techniques through systematic innovation. Colonel Whitfield returned for a second evaluation in June with expectations shaped by the previous year's spectacular failure and professional skepticism about American manufacturing reliability. The military delegation found measurement capabilities that surpassed their original requirements, with environmental control systems that maintained precision under conditions far more demanding than typical manufacturing applications. Repeated testing over several days confirmed measurement consistency that exceeded European standards while demonstrating reliability that military applications required. The successful second demonstration established American precision measurement as internationally superior to European alternatives through systematic engineering rather than traditional craftsman skill. Government contracts followed immediately as military procurement officials recognized capabilities that American manufacturing had never previously achieved. International attention resumed with European manufacturers acknowledging that American systematic methods had produced innovations that traditional approaches couldn't match through individual skill alone. European engineering delegations returned to Hartford throughout 1882 with expectations transformed by reports of American technical achievement that challenged fundamental assumptions about precision manufacturing. British toolmakers found measurement capabilities exceeding their finest workshop standards, while German precision engineers acknowledged American innovations that surpassed European systematic approaches to mechanical accuracy. French metrologists initiated collaborative research projects based on Rogers-Bond, principles that American engineering had proven superior to European alternatives. By 1885, the Rogers-Bond comparator had achieved accuracy to 100,000th of an inch, surpassing original specifications through continuous improvement of environmental control and mechanical precision techniques. American standard measuring machines were being exported to European factories whose craftsmen had previously dismissed American precision capabilities. British armories contracted with Pratt Whitney because American firms could achieve interchangeable parts production using less machinery than European methods required. The global impact extended far beyond measurement technology, as American systematic manufacturing established superiority over European traditional methods across multiple industries. Firearms manufacturers achieved true interchangeable parts production, while sewing machine companies and bicycle manufacturers benefited from precision standards that made mass production economically viable. The Rogers-Bond principle had proven that systematic engineering could surpass centuries of European craftsmanship tradition through innovations that addressed fundamental problems rather than accommodating limitations through human skill. European recognition of American precision superiority marked the end of technical dependence that had constrained American manufacturing since independence. The nation that had fought for political freedom achieved economic independence through systematic engineering innovations that established American technical leadership in global markets. The foundation was established for precision manufacturing advances that would enable everything from mass-produced automobiles to aircraft engines, proving that American systematic methods could achieve results impossible through traditional European approaches to mechanical precision.